Welcome back to our series on statistical methods. I'm Mark Ledbetter. We are in the section for ANOVA and Design of Experiments. This is Lecture 4, Part 5, in Chapter 2. So last time we talked about the hypothesis test, and we actually did an example with our Portland cement example or Portland mortar example. And we used all 5 steps, and we were very clear in all of those steps. And that's the way homework needs to be done. So today we're going to continue, but we're going to look at this in a different manner. So there are different assumptions that can be made depending on the situation. So in real life, you would only choose one of these methods. Only one would be the correct method to analyze this. Last time we assumed that we actually knew the variances and that they were 0.3. So sigma 1 equals sigma 2 equals 0.3, or I don't remember if it was sigma 1 or sigma 1 squared, but we knew one of those, and we said that they were equal, and we knew what they were. Now, the real life case is we don't know what sigma is, but let's say that we have tested for equality of variances, and we've confirmed that they are equal. And we haven't talked about how to do that, but we will. So in this instance, we're going to assume the variances are equal but unknown. So we go to the table that I've given you earlier that says the correct assumptions for the test statistic and the degrees of freedom. So in this case, we're going to use this test statistic, and S of P is given here, and the degrees of freedom equals N1 plus N2 minus 2, which comes from N1 minus 1 plus N2 minus 1. All right, so there's 2 of them. So we start with the hypothesis statement, and I've written it a little differently this time to emphasize something in the test statistics that I did not mention earlier, but I need to. So the null hypothesis is that mu1 and mu2 are equal. That is that mu1 minus mu2 is equal to 0. Against the two-sided test or alternative that mu1 minus mu2 is not equal to 0 or mu1 is not equal to mu2. Now, why do I prefer to write it in this method? Well, we'll talk about that when we get to the test statistic. Okay, but in design of experiments or analysis of variance, we can't just give the hypothesis statement, we also have to give the model. And so we say H1 mu1 minus mu2 equals 0 versus H1 mu1 minus mu2 is not equal to 0 in the model, and Yij equals mu I plus epsilon ij, where I is equal to 1 or 2, and j, it goes from 1 to 10 in this example, at alpha equals 0.05. All right. So now, we have our test statistic that we've chosen because we have n is less than 30 and sigma 1 equals sigma 2 are unknown. If they're known, we can use the z statistic in the standard normal table. When they're unknown and n is not at least 30, we need to use the t-table. Okay, so we need to fill this in. So now look at how I've written the test statistic. What I've done is I've said, okay, the general form of the test statistic is equal to, let's say, theta hat minus theta over the standard deviation of theta hat. Okay, so I need, so this is sigma hat. I'll try to write this clearly. Sigma hat of theta hat. Okay, so the standard deviation of the estimate. All right, it's also called the standard error. So we're taking the estimated value and subtracting the actual hypothesized value. And the hypothesized value is given in the null hypothesis. So mu1 minus mu2 is equal to 0. If you remember, I wrote this in the general form as mu1 minus mu2 equals mu naught. Mu naught does not have to be 0, but that's the case we're interested in this problem. Okay, so that's the reason that I wrote the null hypothesis in this manner, so that I could plug in mu1 minus mu2 into the test statistic. And that value is 0. Now, the authors of the book, they leave this out and they just say this, but that's not explaining to you how we got that. It's y1 bar minus y2 bar minus mu naught, if you will, the hypothesized value of mu1 minus mu2. In this case, that's 0. So 0 gets plugged in here. Okay? So let's do this. Let's complete or calculate this test statistic. I'll clean up a little bit so that not quite so messy. So we need T naught. T naught is equal to y1 bar minus y2 bar. And y1 bar is 16.76 minus 17.04 minus 0. That's the value here. Over. Now, you don't have to put this here, but I'm doing this just to point out how this is related. All right. And in some situations, it will be important, but in a lot of them, it will just be 0. But okay, so now I need to calculate SP. Now, SP is given here as the square root of n minus 1. Well, n1 minus 1. n1 is 10, so 10 minus 1 is 9, times s1 squared, I believe that's 0.1, plus n2 minus 1, that's also 9, times s2 squared, 0.061, if I remember correctly, and they are right here. S1 squared is here, S2 squared is here. All right. And since we're using the squared, we don't need to use this value, okay? These values of S that the authors have given are rounded values, so I don't use them unless I need to, all right, because I'll get different results, slightly different results. So it's more accurate to use S1 squared equals 0.1 and S2 squared equals 0.061. And so that's what I've done. And then N1 plus N2 minus 2, that's 10 plus 10 minus 2, that's going to be 18. All right, let me clean this up a little bit more. Equals, oops, I guess I hit the wrong thing. Happens sometimes. So equals 0.9 plus, and 9 times 0.061, 9 times 0.061 is 0.549 over 18, which is equal to the square root of 0.9 plus 0.549 is 1.449 over 18, which is 0.0805. Whoops. Equals square root of 0.0805. So I can come back over. I'm going to have to unfreeze. Well, sometimes my iPad freezes, so I apologize for that. Okay. So now I can plug in the square root of 0.0805 for SP. Why am I not putting the decimals? Because that's a rounding error. This is exact. Square root of 0.0805 will give me the most accurate or precise results. So 1 over N1 plus 1 over N2, they're both equal. And so we're going to see that the formula reduces. So 1 plus 10 over 1 plus 10 is equal to 2 over 10, which is equal to 1 over 5. When you're dealing with these calculations, simpler is better if it's easy to get there. So this is not a probability, this is an actual calculation. So I do reduce fractions, or this is 0.2, right? So this becomes negative 0.28 divided by the square root of 0.0805 times 2. Remember that when you multiply or divide square roots, same root, square root, then you can combine them. So this times this, and we said that that was 0.2. And so then I will calculate all of this at once in my calculator to make sure that I get the precise answer. Divided by second square root of 0.0805 times 0.2, close my parenthesis, I get negative 2.20670 ... which to 3 decimal places, because that's what my t-table has in it, 2.207. Now I need my critical region. So I have put the critical region here, and we are in the case where we do not know the variances, but they are equal. So variance is unknown, assumed equal by testing. Let me change the color. Maybe that will help. And I'm using the alternative not equal to, which we will use a lot. So we have this as our critical region. So T naught less than negative T sub alpha over 2 N1 plus N2 minus 2, or T is greater than the positive of that same value. Now in our t-table we can only look up the positive. It only has the positives, so be very careful here. So I'm going to write down my critical region completely, and I ask that you do that as well. So I have T naught is less than negative T alpha over 2 comma N1 plus N2 minus 2, or T naught is greater than T sub alpha over 2 N1 plus N2 minus 2. Now, I have a negative value, so I only need this portion. I cannot compare to this because I do not have a positive value of T naught. So it doesn't make any sense for me to try to check that. Obviously, it's not a negative number is not bigger than a positive number. It can't happen. We only have one value of T naught, and I should have said T naught, sorry. We only have one value of T naught, so we need to check the sign of it for a two-sided hypothesis. Check the sign and use that side of the alternative, okay, or of the critical region. So I'm going to actually plug in the values now. Let's see if I can get rid of this without erasing too much. I'm going to change back to blue. I don't like red. So negative 2.207 less than negative. Now I need to look up, well, what's alpha over 2? So T of alpha over 2, N1 minus N2, or plus N2 minus 2, is equal to T of alpha was 0.05. I said that in my hypothesis statement. So half of that is 0.025, and N1 plus N2 minus 2 is 18. So I am looking up this value. Okay? So maybe I'll write that, T 0.025, 18. So negative 2.207 minus, now I need to look up T of 0.025, 18. So I'm zooming in on our T table. 18 is the degrees of freedom. So that is new. So I am on this row. And then 0.025 tells me what column. I go up to the top, I look for 0.025, and I find it here. And so where these intersect gives me 2.101. 2.101, I'm going to plug in 2.101. Now, is negative 2.207 less than negative 2.101? If you have trouble, then please draw a number line. Maybe 0 is here. And then we'll just say negative 2.101 is here. And then we look and it's negative 2.207 is down here. So this is, so it is less than. So this is a true statement. This statement is true. And when the statement is true, our decision, reject H naught, because rejection, criteria is met. In other words, the statement is true. Okay? So, again, because this was my rejection criteria here, I only had to look at the part that included the negative, but I plugged in my test statistic for T naught, and then for this value, I plugged in that value, and so I have this last line here. Negative 2.207 is less than negative 2.101. That is true. The statement is true. If the statement is true in the critical region, then I reject the null. Okay. So if I do reject the null, there does exist sufficient evidence to support the claim. The claim is H1. And so now I have to write the claim in words that the addition of polymer latex emulsion during the mixing process resulted in a different tension bond strength in the units given here compared to the original formulation at a 95% confidence level. The test was performed using a sample size of N1 equals N2 equals 10. Should have underlined that. Okay? Now, I didn't say that it was a simple random sample because this really wasn't randomly selected. We performed 10 trials, and they were in order, and we used them. But it is a sample, but not a random sample. You can think of it as a random sample because this is a small sample using that emulsion and of the population if they decide to do this, and where they use the original formulation, those 10 would be a very small sample of the whole population as well. The randomness is where we have some question. And so you'll see that in design of experiments, randomness of the sample itself is not that important, but the randomization, the order in which things are run, that is important for independence. Okay. So that is that. But before we move on, and my screen keeps freezing for some reason on my iPad. Before we move on, I want to find the p-value of our test statistic. So our test statistic is the negative 2.207. And remember that the t-distribution is symmetric, so I can actually get the p-value, the probability from the upper tail, the positive, and then work with that to get the p-value that corresponds to our test statistic. Now, so here is the table for t, and we said that our test statistic was negative 2.207. I need to zoom in so we can write this. Okay, so 2.101 to 2.552. Our test statistic, 2.207, the absolute value, falls somewhere between these two numbers. Okay? And if we put a negative here, it's still true, right? That it's between those two numbers. It's just that the order should be flipped around. All right. So our test statistic is somewhere between these two values. And so I need to look up at the probabilities, and I need to see if this is the probability for, let's see, there's a, here, do we have it at the bottom? Adaptive with permission. Okay, so this table, I'm assuming that these are one-tail probabilities. And so if this, so we're somewhere between, our test statistic falls in between these two values. And assuming that these are one-tail probabilities, we need to multiply it by 2, okay, each of these. Because remember that the p-value for a not equal to or two-sided test is equal to 2 times the probability, in this case, that that T naught, or T, is less than T naught. Remember, our T naught is negative, so it has to be less than here. Okay? So T is less than T naught. All right, 2 times that probability. Well, that probability is somewhere between these two numbers. So that means that our p-value is going to be between twice these. So twice of this is 0.02, and twice of this is 0.05. Okay, so our p-value is somewhere between 0.02 and 0.05. Alpha equals 0.05, and if you remember, the rejection criteria is p-value less than alpha. So this says right here that alpha equals 0.05, so this says right here that the p-value is less than alpha, so we reject the null hypothesis as our decision, and of course this has to match the decision we made using the criteria, the cutoff or critical region or critical value criteria or method. Okay? So I wanted to give you that p-value and show you that without a computer it's difficult to get with the table, but you can get it. If you're using the computer, you can get the exact p-value. Just remember that you still have to program it to say either the probability that you get or 2 times that. And since h naught mu1 minus mu2 was not equal to 0, that was our claim. This means we multiply the probability of getting a test statistic as far away from the mean as the one we obtained. We multiply that probability times 2. So our actual test statistic will only be in one of the tails. So in this case, we had T naught here. We find this probability that T is less than T naught. But we also are interested in the probability that it being a positive, so the absolute value of T naught is how I'll write that. That probability that T is greater than T naught. We have to add these two together. They're equal, so it's 2 times the value that we got originally. Okay. Now, let's change the assumptions. Let's go back and say, we're going to say that the variances are unknown, but we cannot assume that they are equal. In other words, we tested for the equality of variances, and it didn't pass that criteria that we needed to say that they are equal. Okay. So we're going to change the assumptions here. So the hypothesis statement is now the same. The hypothesis statement here doesn't change, but the test statistic does. So the test statistic now, with the variances unknown and unequal, we can use this test statistic when we have n is small. I believe we're leaving n alone, yes. Okay. So we get our test statistic. I've already filled in the values because you can look at the values and plug into this equation. And you need to do that. So please pause the video and calculate this out and verify the values that I obtained. So with that, a negative 2.207. This is the same value we just got when we use this different formula. Wow. Okay. When we use this different formula here for the test statistic, and we used S sub p for the pooled standard deviation. It turns out that when N1 and N2 are equal, this test statistic reduces to this other test statistic. They are exactly the same. What is different is the degrees of freedom. The degrees of freedom here has to be calculated with this formula, which is just lovely. But up here, the degrees of freedom were N1 plus N2 minus 2. Okay? Much easier to calculate. We have the same test statistic, negative 2.207, but we have a different degrees of freedom. So again, please pause the video, plug in and work out this. It's very important you know how to do this so that you can actually do it for yourself. I say it's very important, but we're not giving tests in this class, so It's actually not as critical as it would be in a different class. The computer is going to calculate this for you, but I would like you to know how it's calculated. So we plug in and we end up with 17.002. We round to the closest one. You could say to go up one or go down. Actually, the correct thing would be to go down to the next, which is what we've done here, to be conservative, all right, with our tests. So we should always go to the, if we get a decimal, we should always go to the whole number for the degrees of freedom. So now we have degrees of freedom of 17. Alpha is still 0.05. Alpha over 2 is still 0.025. We need T of alpha nu, which is going to be T of 0.02517 in this case. Why? Because our critical region, oh, I didn't put it in here, our critical region is going to be T naught less than negative T alpha over 2 in nu, where nu is given by this equation, or T naught is greater than T alpha over 2 nu. Where did I get this? From my chart that I showed you up here. So now we are saying that we cannot assume that they are equal, assumed unequal, and they're unknown, and n is less than 30. And so we still have the not equal to for our alternative. Here is our rejection criteria. Okay. And once you get to understand this, the rejection criteria, you'll be able to do like I can do and just come up with it because you know the form, how it should be. Okay, so let's get back to our problem here, and I need to plug in values. So again, I have a negative for my test statistic, so I only need to look at this half of the criteria. This half doesn't make any sense because T naught is negative. So I have negative 2.207 is less than negative. Please don't forget your negatives. And I need to find T of 0.02517. And so again, 0.025, but now I'm on the degrees of freedom line for 17. And where these intersect is 2.110. So this is going to be negative 2.110. So notice that my cutoff value is different. So I could have a different result, but it does turn out that this is still true. Negative 2.2 is smaller than negative 2.1. So that is true. And again, we reject the null. And while we're at it, let's go ahead and get the p-value. So again, 2.207 is between these two values. And that means that we're going to find the probability that's between these two values, but we need to multiply by 2. 2 times this one is 0.05. And 2 times this is 0.02. And so P is between these, but be careful to reverse it because you want the smallest to the left and the largest to the right. So the P-value, so I'm going to say P-value, is between 0.02 and 0.05. Okay, so the same range of p-values, but there's actually a different actual p-value because we're in a different degrees of freedom. And so this number is closer to this number than it was to this one for 18 degrees of freedom. So that means that the p-value is going to be closer, is going to be bigger. It's going to be bigger for the lower degrees of freedom than it would be for the higher degrees of freedom in this case. All right. So we have our rejection, and again, our conclusion is going to be exactly the same since we again reject. There does exist sufficient evidence to support the claim that, again, the addition of the latex polymer emulsion during mixing results in a different tension bond strength compared to the original formulation, and we did our test at alpha equals 0.05 or a 95% confidence level. using the test was performed using a sample size of N1 equals N2 equals 10. And so this tells us that N was 20, our overall sample size. Well, we'll call it little n, maybe t for total. Okay. So that's it for this lecture video. Please, if you have questions, come to virtual office hours. If you need help before office hours, by all means, email me. I'll get back to you as soon as I can, as soon as it's possible. So please take care of yourself and stay safe, and we hope to see you next time.